All right, so we continue with chapter 17. So the first part, we talked about electric charges, and if there's an electric charge near another electric charge, they exert force on one another. So for example, if I have a charge sitting here, let's call this Q1, and then I bring another charge, so I bring it here Q2, so those two then will interact, and there's going to be push or pull on, let's say, charge Q2. That means Q2, as soon as I place it there, a distance r from the Q1, it will then feel a force. That force either going to be attractive or repulsive, depending on what's the charge of Q2. So if it's Q2, let's say positive, then it's going to be a repulsive, so it's going to be pushed to the right. If Q2, for example, then is negative, right, then there's going to be attractive force toward, let's say, Q1. So that's basically the electric force. All right. So, and the magnitude of the force is K Q1 Q2 divided by R squared. So we talked about this in the first part. What we do here in the second part here is we cover a new concept called electric field. All right, so electric field. Now, electric field is a more abstract idea. So in terms of what we consider for the electric field is this. So let's say there is no second charge, okay? And what we have here is this. So let's say there is just one charge sitting there. What happens when, let's say, you have a charge by itself in this region of space? Does it affect the region of space itself? All right, so the answer is yes, it does. It actually affects the space, the properties of the space itself. That means every point around this charge, if I look at it, right, I'm going to find an effect from that source charge. It's an electric effect, and that effect only on other electric, let's say, charged particles, but still the entire region is then filled what we call with electric fields. And what I can do here is I can then, find mathematical representation of that, be able to calculate the strength and direction of that effect, and then, use it to see what type of, let's say, push or pull effect it will have on another charge. All right, so what we start here is this then. So let's say then we have a region of space, and this region of space then, let's say we have only one charge here right now. So let's say that this charge here is fixed. So that means it's kind of like glued or, stapled, whatever. Like, let's say this charge here is sitting there. So what I'm going to do here is then I'm going to call this a source charge. So this is going to be my source charge. So then the entire space is then affected by this source charge. Okay. Now, what we're going to see here is that this electric field, you can think of like a sort of like, let's say, the effect of this charged particle that is sitting there. So basically the effect of the source charge on the surrounding. Okay. Now, what I have here is this. And if I consider some point P, so then I can find the effect of this particular source charge. Okay. Now, in terms of then mathematical, let's say, representation of that, we're going to see that there's a way for us to calculate. But for now, think like this. The electric field is a vector effect. So it's a vector effect from this source charge. And if I look at that point P, I need to know how far away that point P is from the source charge. Let's say R represents that direction, the distance from the source charge to that point P. Then one of the things I'm going to see here is that this point is different now. That means the properties of this point is different now compared to if the source charge was not there. Okay, that means it's modified. So the entire property of this entire space now it's modified because of that. Okay, now the question here is this: how would I know that? How would I know, let's say, because remember, electric effects, that, they're invisible. You can't really see. So you can't, let's say, see how another particles, affecting another. You will see the effect, right? They're being pushed or pulled. But right now I'm looking at, okay, so here's a charge sitting there, and here's a, some point close to that charge. How do I know, it affects the, that space or not? Well, it's kind of similar to, kind of like, if I give you an analogy, right? Kind of similar to, for example, Earth. So let's say here's Earth. And I'm considering, like, let's say this is the surface of Earth. How do I know that Earth affects all the space, let's say all that space around it? So let's say space above Earth is affected by the, Earth itself. How do I know that? Well, Earth affects things, a different way. So the effect here is not electric. It's, remember, it's a gravitational effect, right? That means, it affects other things that have mass. Okay, because what we have here, the gravitational force is Earth's effect on, let's say, other object with mass. Now, what I can do here is, for example, choose some point P above surface of Earth, and I want to know, well, at that point P, is there effect from Earth? Well, the easiest way to do here is to take an object, I don't know, some object that has mass, and just put it there at point P, and then just let go. If Earth has no effect on that object will just sit there. But if Earth has an effect on that object will be either pulled or pushed from Earth, right? And obviously we know the answer of that. It is then being pulled toward Earth. Why? Because force that Earth exerts on other mass objects, right, always attractive. And remember, the equation for the gravitational force is, remember, again, proportional to the product of the objects times the mass of Earth, m1, m2, divided by the separation of Earth and that object from center of Earth to the center of the object. And if I go and kind of like cancel this, let's say the proportionality sign, make it equal sign, then I have this G, which is the gravitational constant. Remember, this is the equation for the gravitational force. That means Earth, because it has mass, affects other things that have mass. And because it's so much bigger, if I just put Earth by itself, right, it affects all the space around it. That means that point P is affected by the presence of Earth. Now, it is affected even if there is no other object over there, because Earth is there, that point is already modified. That already has the signature of Earth's effect. And the way I can test it, by bringing what I call a test object. I put a test object, right? So let's say I put an object there with mass m. Then I can verify that as soon as I let go of that object, it's then being pulled by Earth. You can do it right now, right? Take a pen or pencil, let it go, and you can see it's attracted to Earth. Why? Because Earth and that object interact. That's a gravitational interaction, and Earth is pulling it, let's say toward it. Okay. Now, if that object is not there, the effect is still there, okay? But that effect at this point, we call it it's not, let's say, there is no force. In order for Earth to exert force, there has to be another object. So what we say is that at that point P right now, there is a field. There's a field, not electric field, but now there's a gravitational field. Gravitational field. And whenever, let's say, I have this, in terms of this gravitational field, right? We talked about that gravitational field actually is that, G, right? The vector G, which has magnitude of 9.8 meter per second square, pointing, in a negative direction. Remember, so this is what we talked about before, not necessarily in terms of this Earth's gravitational field, right? We just said that this is the acceleration or the effect Earth has on other objects. It makes them speed up at that rate. So similar thing, we have it, here. So let's say in this region at that point P, I have a field, right? So this invisible field due to this source charge, okay? And this field also, has a magnitude and direction, okay? But in this case, remember, even this 9.8, it wasn't always constant, right? Further you go from the surface of Earth, that would change. There's a very, small change, but still there's a change depending on how far away you are from Earth. or the surface of Earth. Same thing is here. So we use E with a, an arrow on top, right? Because it's a vector. So this E vector, right? What we call electric field also has, has magnitude and direction because it is a vector. Now, one of the things we have here is, so for example, if I'm drawing the gravitational field right now, it will be like this, in this direction toward Earth, because remember, everything is, attractive. So there is one thing different between electric field, or sorry, electric force and the gravitational force. Electric force can be repulsive and attractive. Gravitational force is always attractive. There is no such thing as, repulsive gravitational force, or at least not, let's say what we're considering. There can be, like, let's say, a repulsive gravitational force, but that's beyond the scope of this class. So it's like, let's say, in a very, very high advanced physics classes where we consider, let's say, that dark matter and things like that could be something like that. In any case, so here what I have then this, just like here I can represent the gravitational field with a, arrow, right? Because it has magnitude. So this magnitude and the direction toward Earth, same thing I can do here with the electric field. That means I can say that at that point, there is this, effect, right, from source charge at that point, and that point generates, electric field. Now, this electric field has a direction, very specific direction, and that direction depends on what type of source charge I have. So let's say if the source charge is positive, then electric field pointing radially away from the source charge. But for example, if I have a source charge that is, for example, so let's say here's my source charge is negative. So let's say let's kind of like separate that. So let's say if my source charge here is negative, then I choose some point P. And I'm like, okay, so what is the electric field at that point P? Or at least in terms of representing it as an arrow. So in that case, the electric field will be toward the charge, the source charge. So that's kind of how the electric field works. Because remember, the electric field, right, is different from gravitational field, where gravitational field always will be pointing toward Earth because it's attractive. Well, electric interaction can be attractive and repulsive. And what we do here is this: whenever your source charge is positive, the electric field anywhere around that source charge, so let's say, how about this, P prime, that point? Well, here's the direction or the distance from that source charge to that point P prime. How about electric field? Well, electric field in this case will be in a different direction compared to this one over here, in a different direction because it's always radially away. And radially away, so to see, this is the radial direction, right? Radial away will be in this direction. And it's actually going to be stronger. It's going to be stronger because you are closer to the, to that source charge. So that's kind of what we're going to be, seeing in the next few slides. So kind of like summarizing that. So here's what we do in terms of if you have two charges, near each other. So you have, let's say, A is the source charge, and B here is the test charge. Test charge. Sometimes what I do here is I put that a subscript, right? That zero subscript next to the charge to indicate that that's the test charge. So Q naught is always the test charge. That means I'm using that to test if there is an electric field there or not. Okay. So then you can see, right, this concept of electric field, right? So, so that means that this electric field right now, there is no, we're not looking at electric field. We're just looking at there's two charges close to one another, let's say separated by distance r, and there is a force. This is just Coulomb's force. This is what we consider in the first, part of this chapter. But now we can look at it slightly from the different point of view. I can say, all right, so here's that source charge. Remember, so here's a source charge. And this source charge, you can see, right, modifies the properties of the space. Everywhere around it, it's modified. That means the properties change, then that means it generates the fields, this electric fields. And if I look at that point P, there's an electric field over there. Okay. We even know right now what is the direction of that electric field at that point P, because I go radial, you know, sort of like I could draw a radial line, right? So that's a radial line from the source charge to that point P, and it's always going to be along that radial line. So along that radial line, either away from the charge or toward the charge. Because our source charge is positive, it will be away from the charge. So this is then the electric field. Okay, and that's always going to be the case. That means anywhere around the positive source charge, electric field will be radially away from it. Okay. All right, so let's look at this. Now what I have here is this. There's this point P over here still, right? But what I do here is I bring a test charge. You can see, right? I bring a test charge to that point. I bring and put a test charge at that point P. Then what happens here is this. Because there was already an electric field, you can then say that electric field is the reason that there is an electric force on that charge. Because the electric field means there is a source charge. Source charge means that, you know, that means that test charge will be interacting with something. So now, what we have is this. The electric field can be then calculated by electric force between those two charges divided by the test charge magnitude. Okay, so this is kind of like the vector format for that. So that means the electric force between those charges divided by magnitude of the test charge. Now, one of the things we have from here is this. Let's say you can see that over there, I don't have any sign for the test charge. Okay, but what I have here is I have this direction. Now that direction is for the electric field. Remember, at this point, the direction of the electric field is independent of what type of test charge I have. See, if I go back over here, see, there was no test charge over there. Electric field is in this direction. If I come back here, electric field is still in the same direction, even if I have positive or negative charge. Okay, what will change depending on the sign of the test charge is the force direction. Okay, it's the force direction. Now, what I have here is then this. So you can, again, so this is the electric field direction, right? That means electric field, again, is radially away from the source charge. That's because the source charge is positive. Then if I take and rearrange this equation, I'm going to get this. Electric force is equals to then test charge magnitude times then the electric field. So you can say this is then another equation that we can use to solve for the force. So that's why it is kind of analogous to the gravitational equation. Remember, gravitational equation is the gravitational force equals a property of the object, test object, the gravitational force depends on, which is the mass, times the effect. And that's the G, right? Times the field. So remember, you can see, right? They are basically equivalent. So those are the intrinsic property of the object. It depends on, right? So electric force depends on electric charge. Gravitational force depends on, you know, the mass of the object. So that means that's why for us, when we're talking about electric field, electric forces, we don't care about the mass of the object. All we care about is the charge of the object. Same thing with the gravitational force. Gravitational force doesn't care about charge of the object. It cares about the mass of the object. But you can see, right, equation kind of similar is that some property like of the object itself, charge or the mass, times the field. Property times the field, okay? The only difference here is that electric force can have two directions where the gravitational force always same direction as the field. Now, here's then what we can see. In this case, this guy over here is the field. Remember, it's going to be away from the source charge. And I'm going to use, you know, capital Q for the test source charge. So this is the source charge. Okay. Now, what I have here is this. So let's say this is my point of interest. And at that point, there is an electric field. There's an electric field already there because of the source charge. But when I bring a test charge and I put it at that point P, then that test charge gonna have a force acting on it. And this force depends on the magnitude of the test charge and the electric field that was present over there. Okay. So now, what I have here is this. Remember, Q is positive, right? in this particular case because I have a positive charge. So if Q is positive, then force same direction as electric field, right? So that means so you can see this equation. So if Q, the test charge, right, that Q naught, if the Q naught is positive charge, and this is true always. If the Q naught is a positive charge, the force on that Q naught always going to be in the same direction as electric field. But here, again, see the same thing, right? Here's the source charge, here's the field, electric field in the direction away from it due to that source charge. But if I bring a negative test charge, then the force acting on this negative test charge is in opposite direction. That's because remember, Q naught is now negative. So if I put some negative over there, right? So you can see then this negative makes the left and right turns as opposite directions. So if you can see, right, if Q naught is negative, then force opposite direction compared to let's say electric field, opposite direction of electric field. Okay, so that's why this is what we have. That means if you have a source charge basically generating electric field, and you bring a positive test charge next to the source charge, if the test charge is positive, the force is in the same direction as electric field. If the test charge is negative, force is in the opposite direction. Okay. Now, if you're wondering, let's say, what happens if the source charge is negative? Well, let's look at it. So let me do it here, kind of like a small picture of that. So let's say this is a negative source charge. Okay. So I take this point P, and I'm saying, okay, so here's the distance to that point P. Okay, so that the R is the distance to that point P. What I'm going to do here is this. Because this is a negative source charge, electric field is in this direction. So this is electric field. Hopefully you guys are okay with that right now. Electric field is toward the source charge if the source charge is negative. And electric field is away from the source charge if the source charge is positive. All right. Now, if I bring then, for example, see if I bring a positive test charge, so my Q naught here is positive. Remember what we said, right? If the Q naught is positive, force is in the same direction as electric field. That means the force will be also in the same direction. Does it make sense? Well, look at it. If the source charge is negative, test charge is positive, well, the force will be toward the source charge, right? Because the negative, positive, they attract each other, right? Negative, positive attract each other. So this test charge will be pulled toward the source charge. Well, what if, let's say, the test charge is negative? Well, if test charge is negative, so let's say it's a negative test charge, then according to this, force will be in the opposite direction of electric field. Well, we already have the direction of electric field toward the source charge. That means now it's going to be in opposite direction, which is this guy here. Well, does this make sense? Again, it does, right? Because negative, negative repel each other. So force is repulsive away from the source charge. So that's kind of what we have. Again, so in terms of then what we're doing here is this. Sometimes you might see here is R hat is a unit vector. And, you know, remember I talked about, let's say, I hat, J hat, K hat, those unit vectors. So this means in the X direction, this means in the Y direction, this is in the Z direction. But sometimes when we talk about the radial, remember radial direction. So here there is no, like, let's say X, you know, X, Y, Z. So radial means directly from the source to that point of interest. So we just use R hat instead of that. So this R hat, you know, we don't really necessarily use it so much in this class. It's just, you know, if you ever see that, you know, just know that this R hat just means that it's in the direction of that, you know, from the source charge to that point P. But the idea here is this. See, here's a positive source charge. Then at that point P, electric field is away from that. Then when I bring a test charge at that point P, it's either going to be pulled or pushed depending solely on the charge, you know, test charge magnitude. Okay. So is it positive or is it negative? Then force will be accordingly. But electric field is independent of the test charge. electric field is due to the source charge, and it's always going to be in the same direction, regardless if there is a positive test charge, negative test charge, or no test charge at all. All right, so electric field, then we have now one equation for the electric field. If you know the force and you know the magnitude of this test charge, you can just use this equation to calculate the magnitude. Or another equation for that, is this. So you can see, right? See over here, if I use this K, let's say here, so let's say I take this Q for the source charge, Q naught for the test charge, divided by R squared, which is the equation for the force, and this divided by Q naught. So this is, the same equation as on the left side. But what happens here, Q naught and Q naught cancels out. That means the electric field is only in terms of K, source charge, divided by R squared, how far away that point of interest is from the source charge. So that's why in this equation, you can see, right, if I have a source charge, so let's say Q, so you can think of like this Q here is the source charge. So any point that I choose as a point of interest, the electric field at that point P only depends on the magnitude of the source charge and how far away it is from that source charge. So that's why it's KQ divided by R squared. We put absolute value to calculate the magnitude, because direction, see, if it's positive, this is the direction. If the the source charge is negative, then electric field will be toward it. Okay, so this is the equation for the electric field magnitude. All right, so now, this is known as electric field lines. That means if I have a source charge, positive source charge, as you can see, right, then I can consider that all the region around this source charge is affected by the presence of that source charge. And there's an electric field everywhere around it. So then any point that I choose, so let's say here's point 1, here's point 2, here's point 3, right? Any point that I choose, there is electric field there. So I can draw the vector electric field. And the electric field always going to be radially away from it, right? So remember, so radially away. And what I have here is, though, see, then electric field is also proportional to 1 over R squared. That means further, point you consider, weaker the electric field. So that's why, see, the length is the magnitude. So the length here is shorter than over here because this point, let's say R1, is smaller than this one, let's say R2. Closer you are, stronger the magnitude, longer the vector. Same way I have then for the negative charge. If there's a negative charge, then electric field always, due to that charge, pointing toward that charge, okay? Again, a point of interest that is closer than another point of interest will have a stronger electric field, okay? Still same direction in terms of radially inward, but, a stronger in terms of its magnitude. All right. Well, what happens if you have 2 source charges? Okay. So now what we have here is this. So let's say here we take Q1, our first source charge, and then I'm considering point of interest as P. Well, remember, so this is R1, the distance from Q1 to that point P. And because the Q1 is positive, electric field here, this E1, right, is due to that source charge Q1. And it's going to be radially away, right, because the Q1 is positive. That means you can see, right, radially away, so in this direction. Now we have then Q2, which means that there's another source charge. Well, if there's another source charge, then that point P is affected now by this second charge as well. That means there's an electric field due to the second charge. And it has to be radially inward toward the Q2 because Q2 is negative, okay? That means for now, just kind of ignore this guy over here because technically that guy here doesn't exist in a way. So what we have here is that there's E1 due to the Q1 and E2 due to the, Q2. That means those are 2 electric fields. Now, electric field is a vector. And if you have more than 2, more than 1 at some point, then what you have here is the electric field at that point P is the superposition of those 2 electric fields. It means like vector sum of E1 and E2. That means what we have here is net electric field. That means you have to add them as vectors. Sometimes even like, let's say 2-dimensional, right? So that means what I do here is I would take this point P, put it in a coordinate system. I can say this is X, this is Y. Then what I have here is then, so let's say right there, right? So if this is my point of interest, there are 2 electric fields over there. Here's E1 and here's E2. And what I have here is, sorry about that. So what I have here is if I'm adding those 2 vectors, E1 and E2, I can use the graphical method, which is parallelogram. If I create a parallelogram, I can see that this guy here is nothing but the net electric field. That means that vector here in the middle, right, is the net effect of those 2 vectors. That means if you put Q1 and Q2 and at those exact positions, they're going to generate 2 electric fields. Here's one, here's second one. But what happens here is this. If I bring a test charge, so let's say if I bring a negative test charge and I put it there, this negative test charge then will be affected by those 2 simultaneously. And it's not going to be moving in the direction of E1 or in the direction of E2. It's going to be moving in the direction of the net, or because of the net electric field. So it's going to be affected by the net electric field, which is in this direction. Now, that means in which direction will this test charge will be, pulled or pushed? In which direction will be the force? I'll give you like a few seconds to think about. In which direction will be the force acting on this negative test charge? Well, hopefully you thought of this direction, upward. Why in this direction? Because remember, when the test charge is negative, force opposite direction, right, of electric field. In this case, let's say the net electric field. That means those 2 together give you this net electric field down. And if the test charge is negative, it will be pushed in the opposite direction. But if, for example, if the test charge was positive, then it will be pushed in the direction of the electric field. Okay, that means it depends on the net effect. All right. Sometimes for simplicity, we can draw these electric field lines. Electric field lines means that, for example, if I have thing like this, if I have here's electric field, electric charge Q. See, then here's point electric field in this direction. Here's another point in this direction. Here's another point in this direction. You can see right then along this radial direction, they're all pointing in this direction. Then you're going to have this. Then you're going to have that. You're going to have this. That means you can simplify and say that electric field lines are kind of moving like this, radially away from the positive charge. Okay, and that's kind of what we have. And this just represents that you can have something like, let me kind of show you this. Here you go. So this is what I was basically shooting for. So you can simplify and say that these are the electric field lines, not electric fields, but electric field lines. Electric field will always be along some, point of interest, tangent to the electric field lines. So if your electric field lines, for example, curves like this, right? See, if your electric field line curves like that, then electric field will be tangent to that, right? So it will be always tangent to the electric field lines. So electric field lines is an imaginary line or a curve whose tangent at any point is the direction of the electric field. That means, more or less we are simplifying, okay? So let's say this will be, if I'm doing tangent to that line, here's the electric field. And that's what I have, right? Here's electric field. But electric field lines give us an easy way of looking at overall, let's say electric field around this source charge. Now, seems like we are losing information about magnitude. Well, technically we don't, because the field lines that are closer to one another, when they are closer compared to, like, let's say those 2 points, closer they are, stronger the magnitude. Further they are, weaker the magnitude. So that's why you can see that electric field magnitude here is stronger than, let's say, over there. And then it's even stronger over there because they are even closely packed. So that means, when those lines are closer together, field is stronger generally. One thing let me do before we go forward. So let's say if it's a negative source charge, an electric field will be like this, radially toward that. Okay. An electric field actually starts at the positive charge. An electric field terminates at the negative charge. It's always, it has a beginning and it has an end. It's a starting point, it's an end point. What happens if you bring those two charges close together? Then they interact with one another. Electric field that was going to go straight like this, now it bends and goes and ends at the negative one. So this one was going to go straight like that, but now it bends and goes and ends at the negative one. So then you get this configuration. So this is actually kind of like a famous configuration known as dipole. So where you have Q, let's say Q1, Q2, right? Two source charges, they have the same magnitude, but opposite direction. So you get something like this. Electric field starts from positive and ends at negative. And you can see, right, you get basically this configuration. You can get something like this if the charges are exactly the same. See, let's say this one goes, but then it bends away because of the presence of the other source charge. And in a way, what I have here is this. So for example, if I look at this point P over here, why is the electric field in that direction? Well, first of all, this is just due to the fact that that point, you know, the tangent to that point P, right? Electric field pointing over there. But why is the electric field pointing over there? Well, that's because if I have this point P, electric field due to this Q1, let's say, will be radially away. So it will be somewhere like this, in this direction. Electric field due to point 2, let's say, sorry, Q2, will be radially away in this direction. But because it's much closer to Q1, the electric field E1 is much stronger than electric field E2. So then when I do the superposition of those, this is what I get. Same thing is here. See, this electric field here is pointing in that direction due to E1. Here in this direction, pointing like this due to E2. So if I do the parallelogram, this is my net electric field. So you can see, right, you can always do the tangent and figure out what are the direction of the individual electric fields. All right, so now we're ready to solve some problems. So what are the strength and the direction of the electric field 2 centimeters from a small glass bead that has been charged to 6 nanocoulomb? All right, so that means what we have here, we have a source, electric source, a small glass bead. So let's take it like this. And the charge here is plus 6 nanocoulomb. Okay, and then we just choose any point. So it says 2 centimeters from it. So let's say here's 2 centimeters, point P. I don't know why it keeps doing that. All right, so let's say then here's point P. Let's say this is R, which is 0.02 meters. Have to be converted to meters. Okay, so what is the electric field? Well, using this equation, K, Q over R squared. So then I have in terms of 9 times 10 to the 9. Then times 6 times 10 to the negative 9 coulomb. Remember, nano is 10 to the negative 9. And this is divided by 0.02 meters squared. Now, let me show you, if you haven't noticed, let me show you like a simple, for example, simple thing that we can do to simplify our calculation. See over here, I have 10 to the 9 and 10 to the negative 9. I can actually cancel those two. 10 to the 9, 10 to the negative 9, I can cancel. So it's just 9 times 6 over 0.02 square. You can always kind of, do that. All right, so then if I calculate an electric field, the magnitude will be 1.4 times 10 to the 5 newtons per coulomb. Why is it newtons per coulomb? Remember, electric field was force per charge, right? Test charge. So Newton for force, coulomb for the test charge. So that was the equation for the electric field. So the units are newtons per coulomb. All right, so this is then the magnitude of the electric field. All right, so then what is the direction? Well, remember, direction here depends on the source charge. Source charge is positive, direction of the electric field radially away from it. That means in this case, it will be in this direction, radially away from it in that direction, right there. All right, so then how about this? How about if I have point, let's say 2 centimeters over here in this direction? Will I get different electric field? Well, I get different electric field in a way that still same magnitude, because you still have that equation, right? Same K, same Q, same distance. It's just the direction now will be different, because this will be then the radially away in that direction. Right. All right, so let's look at another one over here. Okay, so you have 2 point charges that are separated by a distance of 10 centimeters. And one has a charge of negative 25 microcoulomb, the other one is 50 microcoulomb. So we want to determine the direction and magnitude of the electric field at the point P between the 2 charges that is 2 centimeters from the negative charge. Okay, and you have basically a diagram for that. So things like this. So generally one of the biggest problem I see sometimes from this level student is that when I ask students to calculate electric field, they give me electric force. When I ask them to give me electric force, they sometimes give me electric field. So make sure you understand the difference between them. Make sure you understand how you should be calculating and what is, let's say, the difference between electric field and electric force. Remember, so right now I have this. So I have some axis and I have a charge. I have a source charge Q1 and another source charge Q2. So they are separated by 10 centimeters. That means it's 0.10 meter between them, the distance between them. But what I'm asking here is I'm not asking what is the electric force between those 2 charges. In a way I could, right? I can ask you what is the electric force between those 2 charges. Then what you do, you K, Q1, Q2 divided by 0.1 meter squared. Yeah, you can do this and calculate the force between them. Let's say I'm not asking them. I'm asking what is the direction and magnitude of the electric field at some point P, some empty point P, right? There's nothing there. But because these 2 source charges are just sitting there, they affect all the space around it. And this is not something I'm interested in. I want to know that this Q1 creates electric field over there. What is the magnitude and direction of that guy? Compare, and then there's a Q2 generates electric field over there. That means when I look at electric field due to, let's say, Q1, see the Q1 here is negative, right? So Q1 here is negative. That means the electric field due to Q1 will be pointing in the direction of the Q1. It will be in this direction, E1. All right, hopefully you guys understand why. Q1 is negative, right? See, Q1 here is negative 25 microcoulomb. So the charge, electric field is toward the negative charge. Well, Q2 is plus 50 microcoulomb. And it also generates electric field at that point P. It has effect at that point P. In which direction electric field? Well, radially away, and radially away means also to the left, right? So it's also to the left. So this is then E2. Then what I need to do here is, because I have more than one electric field at that point P, I need to calculate net force, net electric field, which is electric field 1 plus electric field 2, all right? That means I need to calculate the net electric field due to those 2. All right, so let's do that. All right, so what I have here is this, and here's electric field. Remember, magnitude and direction, right? And what I can do here is, then remember, I talked about I hat, J hat last time, right? So what I can do here is this. I can see that electric field 1 is in the negative I hat direction. Why negative? Because it's pointing to the left. Then plus, here's magnitude of that electric field 2, direction again, negative I hat. That means this is just E1 plus E2. Those are the magnitudes. And then this is the direction I can factor out. And remember, if 2 vectors on the same axis, you can just basically algebraically add them together. That means I get then K Q1 over R1 square, that's the E1, right? Plus K Q2 over R2 square, and that's basically E2, and then times negative I hat. That means what I'm doing here, I'm adding their magnitudes because they're both in the same direction, you know, and then I'm just gonna give them the direction, which is negative I hat, just means to the left. All right, so then if I'm doing this calculation, then let's see. I can factor out K, right? So I can technically factor out K. That means it's 9 times 10 to the 9. That's my K. And then I do the calculation, becomes Q1 over R1. So Q1 here, remember the magnitude. So we're always using absolute value here. So it becomes 25 times 10 to the negative 6 Coulomb over the distance. And the distance here is this one over there, which is 0.02 meters square. Then plus, then Q2, which is 50 times 10 to the negative 6 Coulomb, divided by distance, which is 0.8 meters square. Then let's say negative I hat. So then what I'm going to get here is this. I'm going to get the magnitude, which is 6.3 times 10 to the negative 10 to the 8 Newton per Coulomb, and then direction negative I hat. That means I can just move the negative in front and put the I hat like that, and then this is what I get. That means its magnitude is 6.3 times 10 to the 8 Newtons per Coulomb, and it's pointing to the left. So that's why negative I hat means a horizontal electric field and pointing to the left. Part B, it says, if an electron, which has a mass of 9.11 times 10 to the negative 31 kilogram, is placed at rest at point P and then released, what will be its initial acceleration in terms of direction and magnitude? All right, so what I have here is this, thing like this. Now this point P, right, that point P, it has an electric field. Now that point P has an electric field, remember, technically then there is this, you know, two electric fields, but we just calculated that, you know, there's a net electric field, right? So there's a net electric field to the left with the 6.3 times 10 to the 8 magnitude. That means this is the net electric field. Okay, so that's the net electric field. All right, so that's the net electric field. And what I'm going to do here, I'm going to put an electron there. Okay. What will happen to that electron? Well, what happens with electron has a force acting on it. Well, that force, that electric force, right? Remember, so electric force is then equals to the Q, remember Q naught times electric field. Now, what is Q if it's an electron? Well, if it's an electron, it's just E, right? It's just E. And what I have here is then, it's a negative E, because it's a negative charge, then times electric field, and electric field here is then, let's say negative 6.3 times 10 to the 8 I hat, right? Now that means what I get here is this. See, the negative cancels that negative, and then my force is just basically E times E electric charge times E for the electric field. That is my equation for the electric force. That means the negatives cancel out, and I can just put the magnitude of that. And it's going to be in an I hat direction. So the force, remember, because the test charge is negative, force is going to be in the opposite direction of the electric field. Okay. Now, we're trying to find acceleration. How do I find acceleration? Well, remember the good old Newton's second law? Net force is equals to mass times acceleration. And that's what I have. Then acceleration equals force divided by the mass. What is the force? Force, the charge times electric field divided by the mass. Right? So that's kind of what we have. And now we have everything that we want, right? We have the electric charge. So I'm kind of running out of room, but let me kind of clean this here and put it there. something like this. So acceleration equals force over mass equals force is then electric charge times electric field divided by the mass. So it's 1.6 times 10 to the negative 19 Coulomb. Then 6.3 times 10 to the 8 Newton per Coulomb. You can see, right, coulombs cancel out. Then divided by the mass, 9.11 times 10 to the negative 31 kilogram. All right, so then what we get here is then the acceleration, which let's say in this case will be 1.1 times 10 to the 20 meter per second square. And acceleration always in the same direction as the force. That means it's going to be in an I-hat direction. Okay. So that's what happens. That means if there's electric field, there's always electric force on a test charge. If there's electric force on a test charge, since any charge, right, electron, proton, or any combination of that, it has a mass. And if it has a mass, it's going to start accelerating because of that force. All right, so here's another example. So we have an electron is released from rest in a weak electric field. Okay, and we're given the magnitude of electric field. E equals negative 1.5 times 10 to the negative 10 Newton per Coulomb y hat. By the way, then y hat is same as kind of like j hat is another way of writing the vertical direction. Okay, so another way of writing vertical direction. All right, so y hat means that this is like, let's say vertical, and then there's a negative means that there's an electric field kind of and it's a electric field that, let's say, pointing in that direction. So let's say the source is really far away, so then electric field in that region is basically pointing down like that. Okay, so let's say all this region is filled with the electric field pointing down. Now there is a good reason that we have this word over there, weak electric field, because electric field here is very weak actually. It's, remember in the electric field in the previous example was 10 to the 8. Here is 10 to the negative 10. I mean, it's very, very small, electric field. So 10 to the negative 10 Newton per Coulomb. Again, this y hat means it's, negative vertical direction. Okay. Now what I have here is this. You have an, electric field over there already due to some source. And then we're going to bring an electron and put it there. Okay, so it says after the electron has traveled a vertical distance of 1 micrometer, what is its speed? What is the speed of the electron as it travels 1 micrometer in a vertical direction? And it also says do not neglect gravitational force on the electron. Remember, any charged particle, electron, proton, or something, there's a combination of that. Any charged particle has mass, and there's a gravitational force acting on it. But electric force is much, much, much stronger than the gravitational forces, unless there is a very weak electric field exerting very weak electric force. And when there's a very weak electric force, that electric force then compatible to the gravitational force, then we have to take it into account. That means here, so let's say if I place an electron here, it has a mass, right? It has a mass. Remember, mass of the electron is 9.11 times 10 to the negative 31 kilogram. And there is a gravitational force. So see, this is Earth. The gravitational force acting in this direction, F of G. Well, now, there is a gravitational force, but there is also electric force. Why is there an electric force? Well, because there's electric field there. And this guy here is the Q naught, right? Our test charge. And this is just an E for electric field. Now, what I have here is this then. There is a force acting then on this test charge. In which direction is the force acting on the test charge? What is the direction of the electric force acting on this electron? What do you guys think? Think about it for like a second or two. Well, hopefully you guys realize that if the test charge is negative, electric force is in the opposite direction of electric field, which means electric force here is in upward direction. So here's an electric force. All right. So then what I have here is then taking up as my positive direction, I can see that this test charge has net force of electric force minus gravitational force, right? Because minus gravitational force, because both of those forces are vertical. So it's in a vertical direction. So Fe minus Fg, and this is equals to m times Ay. Okay. All right, so now I have, this is just a Newton's second law. Okay. So electric force is E times charge times electric field, right? Charge times electric field. Okay. Then minus gravitational force, which is just mg. And then this is equals to m times Ay. Okay. Now what I do from here is then basically in terms of calculating, let's say, the acceleration, which will be electric field times, so electric charge times electric field minus mg, then divided by the mass. So technically then I can take this and calculate then the electric force, acceleration, right? I can calculate the acceleration of this particle. Okay. Or I can do this. So this is the expression for the acceleration. Then I understand one thing, that this guy, starting from this initial position, goes to some final position, and that displacement, right, that delta y, is 1 micrometer, as we're told right here. That means this electron going to be speeding up upward. There's acceleration, right? There's upward acceleration, and it travels 1 micrometer. And we want to know what is the speed after it goes 1 micrometer. So this basically becomes a kinematic problem. Object that is accelerating over some, 1 micrometer displacement starting from rest. What is the final, speed, final velocity? All right, so we're not given any information about time. That means one equation that we can use, and that is time independent kinematic equation, will be this equation: V final square equals V initial square plus 2 times acceleration times displacement. This is kinematic equation. So make sure you guys review the kinematic equations, and you have those kinematic equations on your formula sheets, let's say for the quizzes and things like that. All right, so it's starting from rest. So this guy here is 0. Then what I can say here is V final equals then the square root of 2 times acceleration times delta y, which is then equals to square root of 2 times, well, acceleration, now I can write it like this: charge times electric field minus mg divided by mass, then times delta y. And I can do this calculation. Okay, so that means from here, all I have to do is just plug in the values and calculate. And technically I have all this in the lecture notes, so you can follow that, calculation over there. We should be then getting as 5.8 millimeters per second at the end. Because I have everything, right? I have the charge, I have the electric field, I have the mass, and I have my displacement. Remember, micro stands to the -6, right? Make sure to do all of those, let's say, a scientific notation and everything. So prefixes. Okay, so that means, you will see that a lot of times if you need any information about speed, let's say you can use either kinematics or you can use energy approach. I could have used the energy approach over here too. There's a potential energy, right? As you move upward, right? So there's a change in potential energy, which they can be then converted into kinetic energy and things like that. You can technically also use that. All right, so the last thing we have in this chapter here is concept of flux, which basically tells you, let's say, if you have a region where there's electric field, right? And this electric field then can go through some area of interest. So let's say here's this, you can see, right, electric field lines over there in the picture. And then we just choose some area of interest, and we want to know what is this rate at which sort of like, let's say, this electric field is going through that area. So that means we calculate this flux, which is the product of the magnitude of the electric field and the area of interest. So this is then electric flux. It has units of newtons per coulomb for electric field, then times meter square for the area. Okay, so newtons times meters squared over Coulomb. So then electric flux, a lot of times, is a very useful quantity, maybe not necessarily in the physics 7 class. We actually use this more often in a more higher, let's say, calculus-based physics classes. Is very, very important over there. But here I just wanted to kind of like give you that there is such quantity that we call electric flux, and it kind of goes and represents basically the number of field lines through some area. We're going to look at magnetic flux, and we're going to look at in much greater detail some of the applications of that, but not necessarily like, let's say, the electric flux. Okay, but here's the thing then. This equation, so electric flux is magnitude of electric field times magnitude of the area. And also technically then there's a cosine of theta, and the theta here is in terms of how the electric field oriented with respect to this area. Now, there is this kind of like, one of the ways you can kind of think of this cosine of theta is this. See, let's say, for example, you have this area, and this area has a vector that is perpendicular to the area. Let's call this vector A. So vector A has a magnitude as the area itself. Its magnitude is the area of that, let's say surface that we're considering, but its direction is perpendicular. So sometimes I call, like, let's say n for the normal. N hat means that perpendicular, normal. Remember normal vector, right? Perpendicular to the surface. So that means this vector A over here, if I draw this vector A, you can see, right, it's perpendicular to the surface. Here's vector A. Then this theta here, so think like this. So here's my, surface, right? So let's say this is my vector E, electric field, right, going through that. And then this is my vector A. Then the flux is magnitude of vector E times magnitude of vector A, and the magnitude of the vector A is just the area itself, right? Then cosine of theta between them. See, now both of them in the same direction, so here theta is 0 degrees. So then this just becomes EA. So which basically in this picture over here, right? So EA. But we can also have where the C orientation changes. That means right now, see, this is my vector A. So this will be my vector A because it's perpendicular to the surface. And you can see, right, this is the electric field still going through the area, but I tilt the area a little bit. So there is this theta between them. So in this case, you can see, right, this is then the general equation for that. That means EA times cosine of theta. And now I'm going to get less flux because, what I have here is I have less amount of electric field going through that area because of the area is a little bit tilted with respect to that. And you can imagine, right, if I continue tilting, so let's say if this is my electric field, see if my area is like this, I have then all the electric field lines going through my area. But if I start tilting this area, right, so if I start tilting it like this, then see now I have less electric field lines and I'm decreasing the flux until, for example, I maybe, tilt this the surface such that now the surface is like this, where now this is the area vector, right, perpendicular to that, and this is the electric field. What is the theta now? Well, you can see, right, surface now basically oriented such that vector A and electric field are perpendicular to one another. So theta is equals to 90 degrees. That means then the flux here equals 0 because cosine of 90 is 0. And you can see, right, now no electric field going through the area, right? They're going parallel to the surface, nothing going through the surface. That's because theta here is 90 degrees because surface is parallel to the electric field. That means if the surface is parallel, vector A is perpendicular to the electric field. Or you can say here, see the surface is perpendicular to the electric field, but vector A is parallel to the electric field. But this theta is given in terms of this vector A. So the theta between those two, area vector and electric field vector, right? So it's, you should, you can practice a little bit and, kind of like, get this down. So it's not very difficult, but maybe, a little bit abstract to start with. But that's kind of what we have. All right, so then absolute last thing we have here is looking at what we call conductors. So generally most of the metals are good conductors. And when we're considering conductor, then one of the things we have here is all the conductors, if it's a charged conductor, all the charges are going to be living at the surface of the conductor. And there's absolutely no electric field inside the conductor. So that's the important thing. So all the charges are outside of the conductor, not outside, at the surface of the conductor. So that's why right now there's going to be electric field like this outside of this conductor, because it's a positive, so electric fields are radially away. But then inside the conductor, there is no electric field, because there are no, basically it's kind of like the cavity, right? There's no, no extra charges over there. Okay, so there's no electric field anywhere inside the conductor. One thing we can do here is this. Maybe we can carve a cavity over there. So let's say we have a cavity over there, inside our conductor. Then what I have here is this. If I put a charge inside, then you can see what it does here is, because it is still electric, let's say what I have here is that the charge over there inside, right, gonna accumulate all the positive ones, because it's a positive charge inside, is gonna attract all the negative ones toward this inner surface, and all the positive ones gonna be at the other surface, okay? And we kind of basically get that, okay? So then what I have here is this. So there's an electric field here outside, okay? And there's also electric field like this, okay? But still there is no electric field inside the conductor, okay? So you kind of get something like that, okay? So that means, in terms of looking at, what happens, just remember that if it's a conductor, then electric field is 0 inside the conductor. But if you have, for example, an insulator, then electric field is actually not 0 inside the insulator. You can have a uniform electric field inside the insulator. All right, so that's it for this chapter. Basically make sure that you guys, watch this, and maybe, like, let's say if you have the textbook, look at some of the examples there as well, and then do some of the problems in the back of the free book that I have posted.